The Elbe River, an international port, a cosmopolitan city, with 2 airports, good highway logistics, and plenty of green. This is the city of Hamburg. A vibrant metropolis holds serious security risks. Among them, the dispersion of airborne contaminants in the aftermath of industrial accidents, or a terrorist attack. In a densely populated city, crisis management gets difficult. When a harmful airborne agent is released in a city like Hamburg, both the population and the first responders of the security forces are equally at risk. Consequently, an accurate prediction of the dimension, direction, and edges of a contaminant cloud and of the contaminant's concentration levels is extremely important with regard to fire brigade and police operations, the warning and the possible evacuation of the public, and for the approach of first responders to the site of the incident. Scientists of the Naval Research Laboratory in Washington, D.C. have developed a new software that delivers fast, accurate, and detailed predictions of the spreading of airborne contaminants in urban areas. In a project cooperation with practitioners from the Hamburg security forces, scientists of the University of Hamburg have adapted this software for use in Hamburg and further developed some of its technical aspects using computer simulation, wind tunnel test campaigns, and 2 field experiments in the port of Hamburg.
In dem vom Bundesamt für Bevölkerungsschutz und Katastrophenhilfe geförderten Pilotprojekt Hamburg wird
The Federal Office for Civil Protection and Disaster Assistance helped finance this pilot project to develop a new emergency response management system and to prove its physical validity. During the project, we use an extremely complex computer software to simulate the dispersion of contaminants following hazardous incidents. In order to prove that these simulations deliver reliable and physically correct results, we used laboratory experiments in the wind tunnel as well as 2 extensive field experiments.
Ein Feldexperiment nachgestellt und es wird auch ein Feldversuch durchgeführt.
The project was financed by the Federal Office for Civil Protection and Disaster Assistance and by the Hamburg City Parliament. CT Analyst stands for Contaminant Transport Analyst, and it delivers just that, analysis of the dispersion of a contaminant on your laptop, in your control center or incident room, with a software easy to handle, and all that in an instant. In emergencies, first responders need to make the right decisions as quickly as possible. CT Analyst cuts the waiting time of conventional disaster management software products. In emergencies, it draws directly on a database of tested and pre-computed simulation data, accounting for nearly every imaginable constellation of wind and weather, and far more than 100 contaminants. The dispersion and transport of contaminant clouds in urban environments and industrial areas varies widely. Over water surfaces or open space, they are influenced by different wind flow patterns. Buildings, for example, significantly affect the path contaminant plumes may take. Sometimes, the decay of high concentrations is accelerated. In other cases, it is delayed. When an emergency happens, response personnel need the best measurement and prediction technology available. This requires a profound knowledge of the dispersion of contaminants at ground level in complex urban and industrial environments. This film provides an outline of the methods for simulation and evaluation of contaminant dispersion. It explains the issues of flow and transport in urban areas that can be so critical during an emergency operation. It introduces some main features of the newly developed software, CT Analyst. Now, let's examine wind behavior in atmospheric layers close to the ground, in the so-called wind boundary layer. This includes the complex interrelationships of aerial dispersion in a city such as Hamburg, the influence of local obstacles, the type of hazardous material involved, as well as quantity and length of the release. The large-scale wind, large-scale weather patterns, and the weather during the course of a day, we call that the meteorological cycle, substantially influence the movement of air in the ground layers of the atmosphere. Among others, determining factors are the path of high and low pressure systems, or weather fronts, causing short-term changes in large-scale wind flow. Air movements are strongly influenced by the vertical distribution of temperature, the stratification of the atmosphere. For example, in case of an inversion, we find cold air masses near the ground, with warm air masses above. In this case, air movements can show significant changes over only a few meters difference in altitude. Atmospheric wind flow near the ground is called the boundary layer. Depending on building geometry, time of day, and wind speed, the boundary layer over an urban area can reach an altitude of 1 kilometer. Near the ground, wind flow is interrupted by obstructions such as buildings, industrial facilities, or vegetation. Vortex shedding occurs, enhancing the turbulence of wind gusts and substantially increasing the dispersion of contaminant clouds. Closer to the ground, in the lower part of the boundary layer, yet other conditions apply. The direction and strength of ground wind is influenced by turbulence. This is visible on the twisting steam plumes emitted from industrial smokestacks, which seem to react randomly to wind changes. Therefore, close to the ground, representative wind measurements are difficult. Results will vary widely depending on location and time. Thus, a few isolated measurements in an urban area will not accurately predict the path of a contaminant plume. Within the urban canopy, between the buildings, the influence of wind conditions on dispersion of a harmful agent gets very complex. Emergency personnel will find it hard to assess and react to a situation appropriately. Local obstacles divert the mean wind flow. Here, it is clearly visible. Part of the wind flow is diverted by the building into the street. Another part is pulled sideways or over a single building. The wind flows laterally around solitary buildings. Recirculation zones may develop. In the wake of tall buildings, a vertical flow may develop due to the distribution of wind pressure on the surface of the obstacle. Another typical urban phenomenon are groups of buildings. The arrangement of buildings in cities and industrial areas substantially influences local wind and circulation patterns. As you can see, a longitudinal flow in an urban canyon channels the wind flow, and higher wind speed may occur. Urban canyons oriented perpendicular to the wind direction may occasionally generate recirculation patterns. Streets inclined to the wind show even more complex wind patterns. An angular flow may develop, and, in a common urban layout, is the usual case. Local obstacles influence local wind conditions, and these in turn influence the dispersion and concentration of contaminants. Wind and turbulence determine the speed of contaminant transport, the level and variability of pollutant concentrations at particular locations within the dispersion area, and the time period over which contamination is affecting an urban or industrial area. The nature of the contaminant is another substantial factor. The dispersion behavior of a contaminant is essentially determined by the density of the cloud. A neutral, passive agent will easily drift with the wind field. By contrast, a larger amount of gas heavier than air will remain on the ground or sink to the ground. In turn, light gases or hot fire gases are transported upwards by buoyant forces. And lastly, the duration of a contaminant release influences its dispersion and its impact. Even with a low contaminant concentration, a long continuous release may lead over time to severe contamination. By contrast, an instantaneous release may lead to dangerous concentration peaks, whereas the measured mean concentrations are comparatively low. All things considered, in case of the dispersion of a hazardous agent in an urban environment, emergency personnel face major and difficult tasks. Reliable predictions of short and longer-term developments are crucial. Assessing the situation in an emergency, it is important to note that local concentrations of contaminants may vary widely with time and space. In an open environment, a homogeneous cloud with equal concentrations practically never happens. Instead, measured contamination, especially in close to the source, can rise rapidly in a few seconds or minutes, then sink again. Even during a continuous release, air contamination can vary widely. Thus, in the short term, dangerous health levels may easily be exceeded. To assess the situation, to warn the public, and to approach the site of the incident, first responders urgently need to identify the general area where contamination is to be expected, an important priority, regardless of the level of contamination. There are several approaches to this, such as the well-known 90-degree rule, contamination measurements, Gaussian models, conventional computer simulations, and disaster management systems. When the discharge source has been located and a representative wind direction can be identified, experienced responders use the 90-degree rule for an instant estimate of the danger zone. Starting from the position of the release into the mean wind direction, sectors of plus and minus 45 degrees are defined as the danger zone.
Das heißt, die Schadgaswolke breitet sich
That of course means the contaminant cloud will disperse in a 90-degree angle along with the direction of transport. On location, we have no means to simulate this effect on a computer. That is why we use 4 detection teams taking measurements within the 90-degree angle area and then try to define and narrow down the contaminant dispersion area according to these measurements.
Bestimmen und näher einzugrenzen.
Due to the very complex wind conditions in urban and industrial areas, however, the threat in close range of the release source can easily be underestimated when using the 90-degree rule. Contaminant measurement is another tool for the assessment of a threat. For this, several varying measurement systems, analysis methods, and sensors are available using different spatial and time resolution and sensitivity. We have monitored the dispersion with the remote scanning infrared gas imaging system developed by the Technical University Hamburg. These infrared remote sensing systems allow for the identification of gaseous substances, as well as their quantification and visualization. These gases are in the visible spectrum, transparent to the onlooker. That is, we cannot recognize them. Whereas in the infrared spectrum, they can be detected. In a sense, they do have a color, and that enables us to identify them. We measured the cloud from different positions so as to localize it and follow its transport above the city. That is why we were still able to see the cloud 20 minutes after the release. The advantage of measurements is that they provide precise monitoring of the actual hazard while documenting the potential threat. It is essential to position the relevant technology correctly for effective measurement and analysis. Therefore, all measurement and surveillance duties entail both the monitoring of potentially affected areas, the documentation of potential dangers to the public or to emergency response personnel, and finally, the search for a still unknown release location. When Operations Command has established an initial assessment of the immediate danger, evolving contaminant distribution must be considered. Today, most common tools for physically simplified dispersion simulations use Gaussian models. These simulations usually approach the process of contaminant dispersion in the spatio-temporal average. The influence of obstructions like buildings, for instance, is considered only in a very simplified, averaged way. This is why actual concentrations may be significantly higher or lower than models predict. Meanwhile, ambitious computer simulation programs have been developed. These models directly account for the influence of obstacles near the ground on the dispersion of a contaminant. Complex equation systems are solved using numerical methods. This leads to significantly better predictions, but it also means significantly longer computing time and consequently longer waiting time for results. But even without the necessary preparations, the sheer computing effort of such software products takes anything from a few hours up to several days, depending on the capability of the computer and the size of the model area. On the other hand, the majority of relevant release incidents and practical emergency operations in Hamburg takes less than 30 minutes. This is why such conventional computer simulations are of little use in everyday operations. Practitioners already use different disaster management systems, which are, however, not restricted to the simulation of a contaminant dispersion, but in case of an emergency also deliver additional information, such as data about the relevant hazardous substance, information about specific areas that needed to be protected, information about the number of potentially affected people or possibly particular effects within the dispersion area. When planning the logistics of rescue and evacuation activities, as well as further steps, such information is of course highly useful. However, for the all-round logistical and toxicological assessment of a hazardous spill, Emergency Response Command needs to predict the affected areas, be fast, precise, and continuously updated. This is where CT Analyst comes in. CT Analyst is easy to handle, fast, simple to use, and reliable in its predictions. It's the product of a long research and development process in which fluid physicists from the Naval Research Laboratory in Washington, D.C. and meteorologists from the University in Hamburg worked closely with Hamburg's fire department and police force. The aim of this cooperation was to develop and test a software for the reliable prediction of the airborne dispersion of contaminants in Hamburg. As a first step, scientists of the Naval Research Laboratory in Washington used a high-resolution computer model to pre-compute wind flow in the model area for a variety of wind and dispersion patterns. These calculations not only simulated mean flow and dispersion conditions, they also considered the turbulent eddies that strongly influence contaminant dispersion. The results of these simulations were then given to meteorologists at the University of Hamburg, where the model results were compared with physical laboratory results in the wind tunnel Wotan, testing accuracy and reliability. Finally, 2 large field tests were conducted in an old part of the Hamburg port. Here, data from the computer simulations and from wind tunnel tests were compared with the data of a realistic dispersion in the field. The result, for an area of about 200 square kilometers of the Hamburg city center, CT Analyst can define, without delay, the danger zone following a known release and predict impending developments far in advance. But CT Analyst not only helps to get ahead of a developing situation, CT Analyst offers more. It can help first responders locate the position of a still unknown release source on the basis of information from detection measurements, emergency calls, or information provided by the public. CT Analyst was developed specifically to simulate contaminant dispersion following hazardous industrial incidents, other accidents, but also terrorist attacks. The result of CT Analyst's dispersion simulations can be integrated into existing systems for complex disaster management. Let's take a look at the 2 main features of the tool. First, take the feature Footprint. As soon as the exact position of the containment source is known, it is entered into the tool. Real-time weather data can be entered manually or inserted automatically from other programs. If the specific contaminant is not known initially, CT Analyst will show the expected dispersion, direction, and edges of any contaminant plume. Using time control, the plume's development can be predicted well in advance. When the contaminant is known, its name is entered, and further predictions will take specific account of that particular substance. Different colors show respective concentration levels, while the gray area marks the outer dispersion that may be expected. And here, CT Analyst predictions are always on the safe side. Blue symbols show inactive sensors detecting no containment. Should the cloud reach an inactive measurement point, symbols that were blue earlier immediately turn red. Now take the feature Backtrack. If the hotline receives emergency calls while the exact position of a containment source is yet unknown, emergency response personnel enter markers into CT Analyst, where pollution has been reported, for example, through emergency calls or measurements taken by first responders. Again, red symbols indicate contaminants detected. Blue symbols indicate measurements detecting no containment. On the basis of this information, plus real-time weather data, CT Analyst will now calculate the area where the containment source may be found. At the outset of a chemical accident or terror incident in an urban city such as Hamburg, emergency teams can expect to confront a wide variety of dangers. The expansion of a chemical cloud depends on numerous factors in the complex geometry of urban obstacles. Typical factors include wind direction and gusts, buildings and open spaces, as well as the quantity and length of contaminant release. In the simplest scenario, an open area or far above buildings, the mean direction of the transport of a contaminant cloud will match the mean wind direction. In the vicinity of the release site, however, a locally released cloud or plume will be more or less strongly deflected from the mean wind direction by building-induced pressure fields and turbulences. Characteristically, contaminant concentrations close to the release site will vary strongly. Even at comparatively low mean air pollution rates, high contamination peaks may be reached for short intervals and may significantly exceed average concentrations. Only at some distance from the release site, when cloud or plume envelopes are larger than the surrounding biggest turbulent eddies, more homogeneous concentrations are observed within the plume. Added to that, as the wind continuously changes direction, plumes may easily be separated into several parts, and for the approach of first responders to the site of the incident. Therefore, the transport direction of parts of the plume can differ significantly from the mean direction of transport. The historical part of the port of Hamburg on the northern bank of the river Elbe, next to the city center. Wind flows coming from the river are nearly undisturbed here. 10 kilograms of a contaminant per second are discharged. At the riverbank, about 300 meters from the release site, concentrations under 500 parts per million volume in the long-term mean are being measured, whereas under identical conditions and for short intervals of 30 seconds, mean concentrations of up to 7,000 parts per million by volume are recorded, which is a 14-fold increase. Computer simulations show the high spatial and time variability of the contamination within the dispersion area. Here, CT Analyst marks the entire area potentially affected by the release in red. In typical cases of local hazardous contaminant releases, the edges of the danger zone develop practically independently of the amount released. In case of a real incident, the discharged contaminant plume or cloud will move within the marked danger zone. In this case, As in all further cases, the exact position of the danger zone depends on the actual conditions of the release. Another feature crucial to first responders is caused by specific wind conditions within densely built-up areas. Within such areas, contaminants may actually drift against prevailing meteorologically defined wind direction. This is usually caused by eddies developing in the wake of large building structures. The city model in the wind tunnel is on a scale of 1 to 350. Thus, dispersion is accelerated to 350-fold compared to natural conditions. Accordingly, changes that take much longer in nature will occur within seconds in simulated laboratory experiments. As can be seen clearly here, both the laboratory experiment and computer simulations show the intermittent transport of contaminants against the fixed wind direction above roof level. Consequently, the danger zone reaches far into the direction upwind of the release site, marked red in CT Analyst. After the discharge, contaminants are diluted and channeled. Obviously, with increasing distance to the source, mean concentrations decrease. Again, the manner of the decrease will depend on the actual conditions of release and dispersion. Air turbulences of the approximate size as the contaminant plume or cloud will enhance the mixing of the contaminant with the surrounding air. This results in a corresponding decrease in contaminant concentration. In case of a local discharge, contaminants close to the source will be influenced only in a minor way by atmospheric eddies, mixing and diluting them with surrounding air. Large eddies do not dilute the contaminants. Instead, they change only the direction of the plume or cloud. It is not until they travel a greater distance from the release site that contaminants are diluted, spreading more evenly within the cloud or plume. In areas near the release site, measurements show an extreme variation between phases with low or no contaminant concentration and phases showing high concentrations. These phases vary depending on wind speed and the dimension of the release source. They can run from a few seconds to anywhere around 10 minutes or even longer. This dispersion simulation shows the temporal development of the containment pollution. CT Analyst marks the complete potential danger zone. Different colors illustrate the danger potential as defined on the basis of hazardous incident exposure levels. CT Analyst demonstrates how the contamination levels from a single release decrease over time as they disperse. When a dispersing cloud hits a building, its dispersion characteristics change. For instance, contaminants being transported by wind along an urban canyon can only disperse laterally along the street's path. Consequently, even at a great distance from the release site, higher concentration levels may be reached than in a comparable case with free dispersion. Obviously, the quantity of contaminant released also determines the potential danger in the dispersion area. In this example, the influence of the release rate is demonstrated with a continuous release. The release rate is increased step by step from 1 gram per second to 100 grams per second to 10 kilograms per second. As would be expected, the larger the amount released, the higher the local threat potential within the contaminated area. As can be seen here, the size of the potentially polluted area close to the source does not change significantly. At the same time, contaminant concentrations increase significantly. This shows that as a result of changes in wind direction caused by local air turbulence, even a small contaminant plume can cover a very large area. At the same time, an increase in the quantity of contaminant released can increase the potential danger in the area. That's why CT Analyst also displays the basic danger zone, independent of the quantity of released contaminants. Sudden changes in wind direction or wind speed also influence events. Given a constant mean wind direction above the urban canopy, contaminant clouds between buildings can suddenly change direction. Thus, the danger zone may be greatly enlarged without warning. Urban canyons and street crossings are particularly crucial here. Using the example of a street crossing, laboratory experiments show the change of transport direction within the street range. Due to the scale of the model, all phenomena are speeded up about 350 times compared to the same wind speed in nature. High-resolution computer simulations can also show the sporadic change in dispersion direction of the contaminant plume. As can be seen clearly here, dispersion direction changes randomly within the time of several minutes. CT Analyst takes account of that and accordingly predicts a large danger zone. In the case presented here, it is almost independent of the representative wind direction 80 meters above the ground. Exceptional buildings have an exceptional influence on contaminant transport in cities. That particularly applies to towers reaching far above surrounding structures. As seen here, on the upward side of a wide tower-like building, some air masses are deflected downwards. Thus, even at a greater distance from the source, a contaminant plume can be diverted back into the streets. This means increased potential danger for pedestrians or emergency response teams. At the same time, in the wake of high-rise buildings, a vertical transport upwards may occur. This means polluted air masses are being diverted away from passersby and may instead reach the inlets of a building's ventilation system. These phenomena can also be seen in the computer simulations. Here, the vertical transport of a contaminant in the wake of a building is clearly visible. CT Analyst is based on computer simulations which took account of building heights and their specific effect. Within the software itself, these effects are included, but not visible as such. Here, contaminant dispersion is shown at ground level only. The dispersion of contaminant plumes and clouds are highly variable in terms of both time and space. Turbulence causes random variation in speed and direction of a dispersing cloud. Dispersion direction is especially important if and when observers or measurement probes are placed near the source of discharge and the amount of contaminant released is small. These factors make an accurate prediction of the path of an airborne contaminant nearly impossible. In close proximity to contaminant sources, concentration measurements may vary strongly. In short-term intervals, ranging from a few seconds to a few minutes, extremely dangerous concentrations may appear, even when long-term mean values show only low pollution levels. Air turbulence may divide a contaminant plume into several parts with completely different paths. For this reason, more than a few local measurement sites may be needed to evaluate the actual dimensions of the danger zone. Only measurements taken at a greater distance from the source reflect actual mean contamination levels. In complex situations such as these, CT Analyst is a valuable tool. Its software takes into account temporal and spatial variations of contaminant concentration in a conservative manner. Predictions, therefore, deliver safe results. Danger zones defined on the basis of computer simulations encompass all potential paths a contaminant plume or cloud may take. This is why CT Analyst usually shows danger zones close to the contaminant source to be larger than a single contaminant plume. They are not, however, significantly larger than the actual danger zone. The duration of a contaminant release also determines the potential danger within the dispersion area. We need to distinguish long and continuous releases from short and spontaneous ones. A long, continuous release will create a contaminant plume that will cross various areas at varying times, even if mean wind direction remains constant. The cloud meanders. The longer the release continues, the higher the probability that contaminants will reach all parts of the dispersion area, at least for short intervals. In the wind tunnel, the cloud can clearly be seen meandering horizontally. In the model, all phenomena are speeded up 350 times in relation to natural events. A short-term release is a different matter. It will lead to the formation of a contaminant cloud that may behave much as any part of a continuous release would. But it is also clear if a particular discharge is repeated several times under identical mean wind and dispersion conditions, each may develop its own different dispersion pattern. This aspect is also accounted for in the computer simulations on which CT Analyst is based. The user interface of the CT Analyst does not show differences in marked danger zones. A continuous contaminant release thus accounts for any possible path of individual contaminant clouds. But the actual danger following a contamination also depends on the relevant contamination concentration. If a defined amount of contaminant is discharged for a short period, we may, in measurements very close to the source, initially find higher concentration levels than in the case of a discharge of the very same amount of contaminant in a continuous release. That is because, in case of a continuous release, the same amount of contaminant is already mixed with a larger volume of surrounding air which was passing the release. CT Analyst takes account of this effect as well. In a densely built-up area, polluted air masses may be enriched more slowly. At the same time, dilution may take longer. Wind flow in cities is characterized by recirculation zones within urban canyons and in the wake of buildings. Following the beginning of a contaminant release in an urban landscape, the wakes are enriched with polluted air. But it usually takes some time before contaminant concentrations reach levels that are comparable to stationary concentrations. The period of enrichment can be shorter or longer, depending on different factors. Given a continuous release, relevant factors include the dimension of the release source, wind speed, and, crucially, form and arrangement of buildings. Examples for an urban structure with a high potential for delaying dispersion are, among others, courtyard structures with perimeter block structures, or areas in the wake of large enclosed buildings. During periods of delayed enrichment, first responders can take important steps. They shut down building ventilation systems before the maximum potential hazard is reached. Densely built areas not only have an effect on contaminant enrichment, they can also slow the decrease in contaminant concentration considerably. Even when the main contaminant cloud has passed, remnants may remain in local winds that only gradually will be flushed away. CT Analyst software for Hamburg was developed in 3 stages. At first, scientists of the Naval Research Laboratory in Washington, D.C. developed the software CT Analyst based on a large eddy computer simulation model called FAST-3D. In a second step, meteorologists of the University of Hamburg systematically compared the computed results of their American colleagues with wind tunnel and field test data from Hamburg. The software CT Analyst was examined and validated using systematic laboratory data. The third step began with a major contribution from Hamburg's police and fire departments in April and June 2011. In 2 large-scale field tests in the port of Hamburg, the dispersion of a contaminant was simulated under real conditions. In these tests, the US computer models showed consistent conformity with the Hamburg field test results. Second field test in June 2011. A harmless, invisible tracer gas is released on a fire ship on River Elbe, just off the northern bank in the old part of the port. The first continuous release took 45 minutes. A second short-term release, another 5 minutes. Wind direction was 220 degrees. The resulting tracer gas plume was first visualized and quantified close to the source using remote infrared detection technology developed by the fire department and the Technical University Hamburg-Harburg. At 300 meters to 3 kilometers distance from the source, scientists from the research center Jülich positioned automated bag samplers to sample local airflow. They were analyzed later. The field test results were positive for all concerned. Measurements confirmed the reliability of CT Analyst predictions on contaminant dispersion, even under the complex dispersion conditions in downtown Hamburg. During the field tests, smoke was also released to visualize the dispersion of locally released contaminants. Again, the experiment clearly demonstrated the complex dispersion conditions of an urban city. These shots show clearly how the shape of buildings dominates the dispersing plume. This final demonstration using smoke also shows the strengths of CT Analyst. Emergency response teams need a software that takes account of local building structures, while at the same time delivering fast and reliable results. This is exactly what CT Analyst provides.